This is lecture 11B for Calculus 2 on sequences. In the introduction, we looked at two ways to think of sequences. One is just as an ordered set, and the other is to consider it a function with a discrete domain, and that discrete domain is the natural numbers. So that's what is mentioned here. We can start either with 1 or 0 depending on how you're counting, so we can include 0 as a natural number. Essentially that's the whole numbers, but the idea is that you have this discrete domain, 0, 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, etc. And instead of using the function notation of f of x, let me write that for you here. So instead of using instead of using f of x for a function notation, instead we just do this. We write the value of the term of the sequence, and then we put a subscript 1, and the subscript takes the place of that independent variable because our domain is the natural numbers. And actually we should specify what we're doing, the sequence a to the n, and specify n greater than or equal to 1 or n greater than or equal to 0 depending on the case. The main thing we're going to want to know about a sequence in this chapter is, does it converge? That means, do the terms of the sequence approach some finite number? And we can write that as a limit using the precise definition of a limit, and that's given right here. Does there exist some limit, some number L, in the real numbers such that as n approaches infinity, a to the n approaches L? So in terms of the epsilons, that would be that the absolute value of a to the n minus L is less than epsilon for every n greater than 0, greater than some capital N. That means if you stop the sequence at a certain point, which we're calling capital N, then every term greater than that is within L, the absolute value of that L. A to the n minus L is less than epsilon, or rather all those terms are within L plus or minus epsilon. Then we just call it the limit. If this was a function, we would say it was a horizontal asymptote. But here we just call it the limit. And if the terms converge, we say the sequence converges. And if the terms do not converge, then the sequence diverges. Here's some examples. The first case, we have the sequence a to the n equals n squared. Well, if you just write out these terms, it doesn't take much to see that these are going to diverge to infinity. The first one, well, assume we start with 1, and then 4, of course, 9, 16, 25. They increase without bound. Therefore, this sequence diverges. Here's another way that a sequence can diverge, and that's through oscillations. We have a sequence minus 1 to the n, and so the terms are going to be minus 1 plus 1, minus 1 plus 1, etc. Right, this is an oscillation between plus or minus 1. It never stops. This sequence diverges. And now, here's a harmonic series. A to the n equals 1 over n. All right. These terms approach 0 as n goes to infinity, so this sequence converges. I'll show you the proof in the next slide. So here's our sequence again that we were talking about, the one that converges, and that's the harmonic sequence. Let's list it right up here. All right. So if you remember, the precise definition of convergence is there exists some n, a natural number, that for any epsilon greater than 0, a to the n is within plus or minus epsilon for all n greater than capital N. Here we're going to let, in this case, the limit is 0. So the absolute value of a to the n minus L is 1 over n minus L, but L is 0, so it becomes the absolute value of 1 over n, which is just 1 over n. Now the statement of convergence says that for any epsilon greater than 0, 1 over n is less than epsilon for all n greater than capital N. Obviously, this holds for all n greater than 1 over epsilon, so we could say that for every epsilon, where's my pen here? For every epsilon, if we set n to be any number greater than 1 over epsilon, remember epsilon's greater than 0, so we can do this, then the statement right here holds. Then, let me get the pen again, that would be better. So then all a to the n for n greater than 1 over epsilon, that's the case, So the absolute value of a to the n is less than epsilon. This was just the precise definition of a limit applied to the terms of the sequence. For the proof of the convergence of the harmonic series, we just used algebraic rearrangement to prove that. But we have to use other tools different times, and here's a list of some of them that we use. One is the limit laws. Another is that squeeze or sandwich theorem. We can compare the sequence to a function of a real-valued function. We can use L'Hopital's rule. And then algebraic rearrangement, and that's what we did just now. In addition, there are two new theorems that will be introduced for examining the convergence of sequences. I want to mention here that we spend quite a bit of time working on the convergence of sequence when actually we're more interested in series. But the reason we spend all the time working on sequences is because when we want to examine the convergence of series, we look at associated sequences. So the convergence of a series is related to the convergence of sequences, and that's why we do all the work here to develop these various methods of for the convergence of sequences. So in the rest of this lecture, we're just going to look at those different methods. So I mentioned limit laws. You can apply limit laws to the sequences just like you could apply the limit laws to functions. Right here, and you remember all of the properties of a limit. There's linearity. So we're going to say some sequence an approaches a limit L, and let's say the limit of the sequence Bn approaches M. Then if we want to take the limit of some constant alpha times an plus some constant beta times Bn, of course any of those could be 0, but if we take that limit, it is the same as alpha times the limit L plus beta times the limit n. So if we add two sequences that are convergent together, we get another convergent sequence, and here is its limit. Multiplication, if you multiply two sequences together that converge, it's in the limit, let's just say as n approaches infinity, then that limit is just the product of the two limits. Same with division, as long as the limit of Bn is not 0. And then for powers and widths, it also holds. One thing that has to mention here is if the sequences do not converge themselves, then you cannot use the linearity or any of these limit laws to work backwards. And the classic example is this. So you have a to the n equals, we say 1 over n to the n power, so that this looks like, we're starting with n greater than or equal to 1. So this would be minus 1, plus 1, minus 1, plus 1, etc. Okay, just alternating signs. Now, that does not converge. It diverges because of its oscillations. Now look at this next sequence. Let's say it's minus 1 to the n plus 1, again n greater than or equal to 1. Now this sequence, write out those terms, is going to be plus 1, minus 1, plus 1, minus 1. Okay, it also diverges. But what happens if you add them together? A to the n plus b to the n. Okay, that's going to be, that's a combination right here with the alpha equal to 1 and the beta equal to 1. I just added them together. So when I add them together, I get this sequence 0, 0, 0, 0, which obviously converges to 0. Right. But I cannot use this convergence to 0 to work backwards and say that an and bn also converge to something. They don't. Right. So bottom line is, it's true that you can make combinations of sequences that converge, but then you cannot use the limit laws to work backwards to try to prove the convergence of these sequences here. The limit laws work forward, not backward. The next method for proving the convergence of these sequences is that squeeze or sandwich theorem, and its statement is very similar to the one used for functions. If you have sequences A, let me get the pen or the marker. If you have the sequence a to the n and sequence c to the n, and they both converge to the same limit L, then if there's another sequence that lies between, whose terms lie between the terms of a to the n and c to the n, then the sandwiched sequence also converges to the same limit L. And here's an example of the use of this sandwich or squeeze theorem. Let's look at some sequence. Where's the pen? Okay, b to the n, which is a damped sinusoid that's offset by 25. So this is, you have your decaying exponential here times the cosine. What's the maximum minimum values of cosine? +1 and -1. So the greatest that this can be is 25 plus 15 times e to the minus 0.2n. So in other words, if you replace cosine by the maximum that it's going to be over the entire sequence, then you have found another sequence, in this case, because we have the n attached to the e, we found another sequence that's always greater than our initial one here. Now what's the minimum is -1. That means we can find another, so we have now found another sequence that's always, whose terms are always less than our original sequence. This is commonly done when you have sine or cosine. You've got some function that oscillates between a maximum and minimum value. Then this decaying exponentials out here, you can place the cosine by its maximum value of +1, or whatever it is for the particular function that you have here. By its maximum value, that will give you the function that's greater than your original function. Then replace it by its minimum value. In this case, it was -1, and now I got the function that is always less than the original function. Right. So made a note here, if exponentials aren't available, so you like having this decaying exponential. If that decaying exponential isn't available, then look for either the harmonic sequence 1 over n, or a term with the generalized p sequence 1 over n raised to the p, where p is greater than 1. Both of these will converge to 0, and if you can sandwich your original function between those two, then you've created the criteria for the squeeze theorem. So in this case, we have set it up. We have a function whose terms are always less, or a sequence whose terms are always less than our original sequence, and another sequence whose terms are always greater than our original sequence. Now the two outside sequences have to converge to the same value, and they do. They converge to 25. So the original sequence converges to 25. And here's a graph showing just exactly that. In the blue, in here, that's the 25 plus the decaying exponential. I can't remember how it was scaled. Was it 20 e to minus something or other, 0.02 n? It doesn't matter. You have a decaying exponential times the cosine of n. And although this is written with a lot of dots, it is a discrete function. Okay, so here it is decaying down, and the one we constructed, the sequence we constructed by setting cosine equal to its maximum value, is right here. And it's decaying to, it's converging to 25. Here is the one with the pluses, and that was the one that was always less than the original sequence. So, oh, I'm sorry, it was a negative sign here. Well, let me start that over. Okay, it was 25 minus, I said promise, okay, 20, and then the decaying exponential. So again, the sequence, the squeeze theorem is very useful when you have a decaying, you have some either decaying exponential or a p or a p sequence or a harmonic sequence in a buried in a sequence where you have another term like cosine or sine that has a maximum value and a minimum value throughout the whole sequence. Like I say, it's easy to see graphically. Another useful way to determine convergence is to compare the sequence to a corresponding function. So many sequences can be compared to a real value function, except those containing factorials. Well, let's look at an example of a sequence that can be compared to a real valued function. Here we have a to the n equals e to the minus n over 2 to the n. All right, that's the discrete domain. N is a natural number. The corresponding real valued function is e to the minus x over 2 to the x. Then you can look at the behavior of the function, and from that determine the convergence or divergence of the sequence. So if you look at the function itself, the limit as x goes to infinity of 2 to the minus x times e to the minus x is 0. it converges to 0. Its horizontal asymptote is 0 when you think of the function, and the sequence follows suit. It also converges to 0. And here, this slide shows exactly that. The sequence, e to the minus n divided by 2 to the n, that is shown here by these dots. This is its value at 0 because remember it has a discrete domain. Here it's its value at 1, at 2, and at 3. The real valued function is e to the minus x divided by 2 to the x, and of course it's shown by this continuous line. You see, it converges to 0, taking the sequence with it. You don't always have to rewrite the sequence in terms of real valued. You don't have to always replace n by x. That's what I mean here. You can use, for example, you can use L'Hopital's rule directly. So here we have the sequence log n over n. We want to determine the limit as n goes to infinity of log n over n. Well, we could write this in terms of log x over x, then take L'Hopital's rule, but we can just go right ahead and use it anyway. We notice that as n goes to infinity, log n, of course, goes to infinity, and so does n. So we have infinity over infinity, which is an indeterminate form. Therefore, we can take the derivative of the numerator and divide it by the derivative of the denominator, again taking the limit, and we end up with the limit as n goes to infinity of 1 over n, and determine that the limit is indeed 0. So this sequence converges. And again, we didn't translate it back to a real valued function and then use L'Hopital's rule. We just went ahead and used L'Hopital's rule.